So next up is Dr. Ryan Watkins. She's a research scientist at PSI, and she's going to give us new insights into the lunar surface from LROC NAC-Scale photometric investigation.
Thank you. I am not able to share my screen right now.
Bethany, I think you'll have to stop sharing your screen for her to share.
Oh, yeah, there we go. Let me pull it up real quick. All right, are you seeing my slides?
Yes.
Okay, great. Yeah, so I'm not going to be talking about an actual mission or mission concept. Instead, I'm going to talk about some really neat science that we've been able to do with an ongoing mission, specifically the Lunar Reconnaissance Orbiter and some neat investigations we're doing with the camera. So I'm going to talk about using NAC Photometry to understand the physical and compositional properties of the moon. So for those of you who may not be aware of what photometry is, it's essentially just studying the reflectance properties of the surface and what those properties tell us about different physical and compositional properties. So there are a lot of different factors that affect how a surface scatters light, such as composition and mineralogy, glass content, surface roughness, space weathering, etc. So one of the reasons that we use LROC imagery is that it gives us the orbital data necessary for these photometric studies. Specifically, we have repeat imaging at different illumination conditions of the same areas. And this really allows us to do some good photometric modeling. When you combine LROC imagery with narrow angle camera scale digital terrain models, then we can determine photometric parameters at the DTM scale, so 2 to 5 meter per pixel. So these photometric parameters will depend on different things like composition or physical properties. And then just at the bottom here, you see that combining photometric data with LROC NAC images, and then coupling this with Hapke photometric modeling and Apollo soil data can really enhance our understanding of the geology of the moon. And hopefully I will convince you of that with the rest of my slides. So here's the slide that I'm sure everybody was really hoping I would show, but lucky for you, I'm not going to talk a lot about it, but this is the Hapke equation or a form of it. So we use Hapke photometric models to fit reflectance data from the NAC images. The Hapke reflectance models are some of the most widely used for interpreting regolith properties from spacecraft data, and they provide very good fits to the observations we see with the NAC images. So really all you really need to know here is that there are a few key parameters that we're interested in. Here's a single scattering albedo up here. This is largely dependent on composition. And then the B and C parameters, which are sensitive to backscattering characteristics and are really just controlled by physical properties like grain size, grain shape, glass content, and things like that. So for the work that I'll show you in the next few slides, the inputs that we need to determine these parameters are the NAC image itself, which has the reflectance data, or I over F, as you'll see the reflectance listed as. Then we need the illumination conditions at each pixel. So these are the incidence, emission, and phase angles. And we are able to calculate these using the NAC digital terrain models and slope data. And then finally, just some other model assumptions and parameters that we derive from empirical and experimental data from other works. So again, just most of what I'll show for the rest of the talk will be a single scattering albedo, but I will talk about B briefly at the end. All right, so then this is just another schematic showing how we take reflectance data from the NAC image coupled with the digital terrain model, which allows us to derive local geometries for each pixel, so local incidence angles, local emission angles, and local phase angles. And these feed into the Hapke equation as well. And this allows us to output parameter maps. So the one I'm showing here is a single scattering albedo parameter map. And again, this is on the scale of the DTM, which ranges from about 2 to 5 meters per pixel, depending on the actual DTM. And this allows us to really get at physical and compositional parameters at the meter scale or the outcrop scale. So now I'll move into telling you how we're using NAC photometry and these parameter maps at different sites of interest across the moon. So one of the best places to start with is the Apollo sites, because we have very extensive NAC coverage of these areas as well as sample data. So, excuse me, Tim Hahn created a regional scale single scattering albedo map of the Taurus Littrow Valley, which you see here in the corner. And you can see the different colors basically correspond to variations in single scattering albedo, which also correspond to largely variations in composition, but also some in maturity, which I'll touch on briefly. And I will just apologize in advance. The color schemes for each of these maps is going to be just slightly different from one another. We haven't really standardized the best way to display these yet. And I've been trying to I'm in the process of converting a lot of them to colorblind friendly maps. So again, they'll be slightly different slide to slide, but just bear with me. You will see they're largely on the scale of 0 to 1. So what Tim Hahn did is he took images at the Apollo 17 site, again, created this parameter map, and then he correlated over, I think, 30 plus sample stations worth of data with the single scattering albedo. So here, this plot is the single scattering albedo as a function of mafic mineralogy, so FeO plus MgO plus TiO2. And here, the blue line is a linear correlation to the mature Apollo 17 samples. You can see there's a pretty good fit between mafic content and single scattering albedo. Now, you do see a few effects here kind of becoming a little bit obvious. There are effects from maturity. So immature soils tend to plot kind of above this relationship. And we're also looking into the effects of glass content on this curve. So that's kind of a work in progress, but we do definitely see some effects of maturity. So one key thing we really wanted to do with this was constrain the more feldspathic end of the curve. These other Apollo sites, these values are from some older work I did with blast zone studies. But we really just want to kind of get a better constraint on this end of the curve. So that's what we did. So the thing I've been working on the last, I guess, couple of months is the Apollo 16 site, making parameter maps here. So here you see the single scattering albedo map again. Here's the landing area and the different EVAs, as well as the B parameter map on the right, or my right. So you can see that the effects of maturity show up pretty distinctly. You get the rays of North Ray and South Ray crater, which are very immature, and they show up very distinctly in these two maps. So similar to Tim Hahn, I went in and extracted sample data for each soil sample. Primarily, I got mineralogy, grain size, and maturity data, and then correlated this with the derived single scattering albedo values that we got from the NAC images. And then, so here is the slightly updated plot. The fit has been slightly adjusted and is slightly better. So we've kind of begun really constraining this more feldspathic end of the curve. And again, you do see the effects of the immature soils really standing out here. So these are samples from North Ray on the immature ejecta. So these kinds of relationships are very useful for inferring the compositional and physical properties of other areas on the moon that we don't have ground truth data for. So I'll show you a couple of examples of places where we're kind of applying this. I won't go into all of the sites we've used this on, but hopefully I can hit a few interesting ones. So the first I'm going to show is the Apennine Bench Formation, which is likely the only large province of exposed creep basalts on the lunar surface. So this is work that's largely being done by Sarah Valencia. So she's using a combination of LROC photometry and M-cube mineralogy data to look at the compositional variations at the Apennine Bench. And the preliminary results so far seem to suggest that the mafic contents within the Apennine Bench are remarkably similar to those seen in Apollo 15 creep basalts, likely indicating that the Apennine Bench formation is volcanic, likely volcanic. And again, this is the same plot that I showed before, but now we've got the different materials within the Apennine Bench region plotted here. We can also use these correlations to investigate exposures of pure anorthosite on the moon with the goal of better understanding the distribution of crustal rock types at the NAC scale. And I'll kind of talk through this quickly, but if you want more information, there is a poster by Brad Jolliffe this afternoon. So you can check that out for some more details. But if you're not familiar with pure anorthosite, basically we have hyperspectral imaging data that suggests there's anorthosite in very high percentages, so about kind of greater than 95% plagioclase. And Anna Schoenwald went and looked at a few of these areas of pure anorthosite detections and correlated their single scattering albedos with iron content. And based on her correlations, she found that most of the plagioclase areas didn't really exceed 95%, most of the pure anorthosite areas didn't exceed 95% weight plagioclase, likely indicating that there are other makefit components present among these anorthositic rocks. And again, check out Brad's really great poster and audio recording if you want more information. So again, I haven't talked a lot about the B parameter yet. We're still kind of working on establishing some of the quantitative correlations between the B parameter and physical properties, but we are starting to look at it, especially in context of Lobate Scarps. So this is work being done as part of the Survey-Trex team. We've begun a comparison using OMAT data and NAC Photometry to analyze the various surfaces around Lobate Scarps and other tectonic features that have possibly been recently active. So we're looking at what the B parameter can tell us about surface changes here, and then whether these surface changes could help inform or benefit future exploration. So here I'm showing an example of the Henderson scarp. Here you just see the reflectance data from the NAC image, and then the single scattered albedo and the B parameter. And as we would expect, we don't see any real variations in single scattering albedo, aside from those that we may see with maturity. So again, we don't expect any big compositional changes. But we do notice that we do have some distinct differences in B values right along the scarp face for many of these locations. We're still kind of teasing out what this may mean, but variations in the B values could likely indicate physical changes that were induced by seismic shaking. So differences in perhaps surface roughness, or maybe changes in grain size or grain shape that was induced by the breaking apart of particles during these seismic events.
And if we could wrap it up soon, Ryan, that'd be great.
I can do that. This is my last slide. So just to conclude, I hope I've convinced you that photometry is a very powerful tool that has many useful applications for studying the lunar surface. Correlating photometric parameters with Apollo sample data is really useful for helping us understand physical and compositional properties of areas of interest. And here I've just listed examples like using single scattering albedos from Apollo 16 can inform pan mineralogy, or Apollo 17 Bay values at different areas, such as maybe the Lee Lincoln Scarp can inform Lobate Scarp properties, and much, much more. But really ground truth is key. So we really need more samples to bring back so we can correlate with remote sensing data. With that, I'll thank you.
All right, we'll take the questions if there are any in the discussion time.